Hello dear students, today's teaching week 7 and I wanted to catch up with you on some matters that were left undiscussed during the previous week and also during that week. Specifically, I'm really worried that you are not good with Excel, and for you how to develop curves can pose a problem. Curves, visuals, generally in Excel the visuals are a very helpful tool to illustrate the dependencies between one time series or just data columns and in other data columns. So let's learn how to develop charts in Excel with respect to your last Friday's tutorial, in which you had to associate different types of costs, 3 types of the total cost, 3 types of the average cost and the marginal cost, with the quantity of the output generated by the employment of labor as a variable factor. That was a variable factor generating variable total output, and therefore, because there was a law of diminishing marginal product assumed in that exercise from the last Friday teaching week 6 tutorial, right? It was an exercise with a law of diminishing marginal product in mind. The product here, the total one, is increasing, but the marginal product is declining, right? Diminishing. So with that exercise, we had a very typical shape for the cost curves that resulted here for the total cost, for the average cost, for the marginal cost, and plotted here. We plotted different, pretty much different curves. These dependencies were plotted as curves on this cost and Q space. On the y-axis we had cost, and the x-axis we had quantity, not of labor employed, but the quantity of the output produced, right? So it's that Q depicted here. So just let me show you one more time on the record how to develop this sort of a chart. Let me first cancel it, and we'll try to replicate the process through and through, step by step. Okay, so first you need to develop a visual associating just one type of a cost with a total output. For that you need to develop a scatter plot. When we associate two quantities, that quantity with some other quantity, you want to plot z as a function of z. What you've got to do is to use a scatter plot visual, a scatter plot chart here. But first of all, of course, you have to select data inputs, including their names, including the column names. The column names should be right above the data series, and hold to select both of the data series spaced out at a certain interval from each other. You have to hold the control button down, right? The control button should be kept down whenever you select. So I'm selecting this X and this Y, holding the control button down all the while. And with that done, still holding the control button out now, right? I can release it now and go to insert. And again, you can use this scatter plot. We have that recommended chart. All charts, okay, remember scatter plot, right? And of which type? Not just points, but let me select, right? It was a good selection, I guess, like that, right? Like that. Okay, good. So step number 1 is performed. The first association is depicted. The association between the average cost and the total output. Step number 2 is to just mention, let's mention the name of the axis. Here we have Q of the output. Q of the output, not labor, but output. On that axis, we have different types of costs, different types of the same costs. Because we'll continue to populate the cost and Q space with different curves, so just different types of costs, not just the average costs that we have been dealing with. And let's call this chart, okay, no, it's not an average cost anymore, but costs depending on step number 2. Okay, is to add up more lines. We can add up just as many lines as we want. Right now we have the average cost plotted, the average total cost, right? Let's also indicate the average fixed cost on this chart because it's going to decline like that according to that spark line. select. Now I don't have to select two columns, just the column I'm adding to that projection between Q and the costs, right? So every time I add up one extra curve, just I select one column. Now no need to select two like previously. The first association was already set up, established. We just add up new associations to the existing projection between the costs and the Q. That's what we are projecting, the dependency of the costs on the Q of the output. Okay, select. Now you don't have to hold the control key down because it's just one column, so no need to hold the control key down. Okay, average cost, go to the chart now, to the chart plane, and on that plane, somewhere in the blank space here, just paste, right? No, something wrong I did. That was the average cost. Now I'm selecting average fixed cost, right? Copy. I have to copy, of course, the selection, and then go to a blank space on a plane and paste, right? Okay, now I have one more curve added to the plot, to the chart. I also want to add my, let's say, marginal cost. This time around, that's a marginal cost I want to add, including their names. Again, select with the mouse, copy, right click and copy, go to the chart plane, select the blank space and add, right? So this gray area, the marginal cost is now added, the gray line, sorry, the gray line, the marginal cost line is now added. And now we have three charts on the plane associating cost and the Q of the output. So it's time to add up a legend to the chart so as not to be confused. Legend, again, how to add a legend, go to the right hand tip of the chart, click on it, and there you have this plus signs, click on it one more time, and go to legend and click on legend. And now the legend is added to the chart. Okay, now let's continue adding more charts. What if I want to add up my total costs, the total, all the costs, right, to my depiction here, to my chart here. Okay, I select total costs as usual, so right click and copy in an attempt to add up to the chart. And now the whole thing collapses because the scale collapses, okay? The scale collapses. This is a big amount, it's total cost of all the products up to the maximum quantity of goods produced. And these are like mostly average costs, marginal costs. They are stated on the per unit basis, so they're small amounts. But the total keeps adding up as you go on the Q-axis. The more you move to the right, the more is your total cost is increasing by. Right? So we have a scale problem, a breakdown of the scale. How is it going to be fixed? Okay, right now our chart type is the scatter plot, right? The scatter plot. As you remember, when I set up the chart, it was set up as a scatter plot to associate two dependencies, just one dependency between Z and Z, right? And then I added up other dependencies on the same relation between the costs and the Q. But now we have a breakdown because the scale problem arises. So we have to change the type of the chart. It's very easily done. We have to change from the scatter plot to combo, to the combo type. In order to be able to add up one extra axis on the right for the total costs, and then we'll have just two axes, not just one anymore in terms of the y-axis, but two y-axis. How it can be done? Okay, so you go select, right click, select the chart, right click on it, and change a chart type. Here you have it. Click on the change the chart type and select combo now. Not anymore as a scatter plot, but now we'll design a combo chart to address the breakdown of the scale issue that you notice here, right? And then everything will be restored to the proper scale. There will be no issues with that. So, okay, we have average cost curve plotted as a line. I want all my functions, all my dependencies to be lines. So, of course, I select lines for all of them. I don't need any new depictions like bars or something. Clustered bars, clustered lines, just lines everywhere. My functions are lines, okay? But now, whilst for averages and marginals, right, for the average and marginal costs, I have my primary axis. For the total cost, I will add up my secondary axis, the total cost line, will be plotted on the secondary new additional axis. Click, and the secondary axis is instituted. Now we have two axes. Now we have the left axis for average and marginal costs, and the right axis for, and obviously we need to adapt. Can we adapt? There's a title for the new axis. I'm not sure if we can. Yeah, we can. Just clicking on this plus sign in the right hand corner of the chart again, and again clicking on the axis titles. There's now a box opened up for the new axis that we introduced to the combo chart. Let's call it like the total cost, right? It's the total cost, right? The yellow line that was having a very big number scale. Okay, so now we have indications for our axis, and here, while we were at it, this indication collapsed, so we have to redo it. Here we have average and marginals, right? And here we have Q, right? When we edit up axis titles one more time, everything has collapsed, so our prior notation has also collapsed. Q of product. And I redid it, so now we have it stitched and patched. Stitched and patched, perfect. Okay, so we have a legend. We can just shift it and redesign the space of the chart as the way we like. Maybe we can shift it down like that. Maybe we can do one more thing and put it on the top. I don't know how it's better to design it. Let's put it on the top, the legend, right? Maybe like that it will be better. Yeah, like that I think it will be better. Like more visual. Okay, so the legend goes on top, and now we have different types of costs plotted depending on the product output. Everything except for the yellow line, the three charts, they relate to either averages or marginals according to the legend, but the yellow line is your total cost line, and the total cost line has a separate projection on a secondary axis because it projects big amounts, the total cost. And here we have averages and marginals, which are small, like not tiny, but rather small amounts, not hundreds, but just tens of dollars. Here for the total cost we have hundreds of dollars, here we have just tens of dollars, so we have two axes with different scales for different graphs, right, for different functions, plotted on the same cost and Q space. This plane, right, this space is now populated with curves with different scales. Again, remember, first design the scatter plot and then shift the type of a chart to the combo type to adapt the secondary axis when you have the scaling problem. And just to redesign, always remember you can adapt some extra things, the axis titles, the legend here, right? As you click on the plus sign, always you can adapt some refinements to the chart, but the basic type from which you proceed the development, right? The scatter plot under insert tab here. And then I switch the scatter plot to the combo type, having added additional lines one by one by copy pasting them, selecting the area and copying. For example, for the variable costs, we can also now add variable costs because they are not yet depicted. Total variable costs are not yet depicted, so I'm copying, right? Copy and paste on the blank space. And because it has a big number, it obviously should be read on the right scale, right? The difference between these straight lines is your fixed cost, the total fixed cost, right? This is your total cost, and that's total variable cost. The difference is the total fixed cost. By the way, you can also add the total fixed cost, which will be just a flat line to the chart, selecting, including the title, copy, pasting, clicking on the blank space and pasting, right? We now have that line, the green line, right? For the fixed costs, it's plotted according to which scale? It's 200, right? So it's on the right scale. Like all the totals, the total, the total variable cost, and the total fixed costs, they are plotted automatically on the right axis with respect to the right axis, and the averages and the marginals are plotted automatically with respect to the left axis. Here we didn't change anything. So that's how you design the graphs in Excel, which is a very helpful skill, I believe, to associate, just to give a visualization for relations we observe in the tabular form. We can just as well restate the relations in a graphical format like we did using these tools for the charting. Okay, so I want to catch up as well on what we did for this week with respect to marginal cost analysis. We did something to illustrate the marginal cost and profit rule. So the marginal cost curve, the marginal cost generally are very important because I show you the shape of your supply curve, of your individual supply curve as a producer. So in a very simple case where we have marginal cost not anymore given like here, our marginal costs here are which ones in that tutorial example? Like this gray curve. The gray curve is your marginal cost, and that's a curve almost because we have not a line anymore but a curve. It's a nonlinear relation. But here in a more simple case, you can just imagine that our marginal costs are just linearly related to the quantity of the output. And here I have an example for you. For the same association, you produce the first good at the cost of $1. You produce the second good at the cost of $2. So here is your marginal cost. Of course, we are plotting not the cost, but the cost of that very good, meaning the marginal cost. The marginal cost, if you remember, is that thing. Marginal cost is an increase in total cost associated with a change in the output by 1 unit. So I'm plotting that marginal cost, the cost to produce that very second item, that very third item, and that very fourth item here. The second, the third, and the fourth items to be produced each have a cost related to that item, the marginal cost. The cost of the second, third, and the fourth item. $2, $3, $4 is just an example. $5 to produce the fifth item, and $6 to produce the sixth item. Now we need to decide how many items to produce in our business. Again, this is done with reference to the market price prevailing for the items we are making. On the market, the items that say they are sold at $6 each. The market price is an exogenous, it's given from the market information. We know on the market you can sell our output no matter how many goods you produce, each will be sold at $6, meaning each, right? Each. $6 each. And so knowing the market price plotted on that axis, right? It's also like a combo chart. On one axis or to the left, we have the marginal cost of our production process. On the right axis, on the same chart, we plot the market price MP. And the market price is your, every time you sell, every time you make a sale, it's your revenue, right? Your revenue. So you add up one extra sale to your revenue. So then your marginal revenue will be your price received on the market. Marginal revenue is a price is an additional revenue per one good sold, right? The marginal revenue, that thing is what is by definition. The thing is MR is a marginal revenue. Okay, that thing, right? MR and marginal revenue is a revenue you receive for each additional item sold, right? You sell it at the same price, $6 each. So every time you sell one extra item, you will get $6 as an addition to your revenue. So your marginal revenue is the same as the price, right? That's why I'm associating a price with marginal revenue is the same thing. In the situation when the price is same for all the goods sold on the market, $6 each. The price and the marginal revenue is the same. So it's an axis for both the price and the marginal revenue because the two things in that setting are identical. On the right hand, we have that vertical axis. Here on the left hand side of the chart, we have the marginal cost projection. Again, the marginal cost is $1 for the first item, $2 for the second, $3 for the fourth, and so on and so forth. And then the market price for all the items is $6 each. How many items will we produce? Question mark. The optimal quantity to be produced is decided by the analysis. Again, for the first situation, compare the idea of producing the first good with its price at which it can sell on the market. It's $6, right? So the first good to be produced will fetch $6 on the market, and it will cost you just $1. That very first good will cost you $1. The profit you will make selling it will be $5 of profit, because you sell for $6 and produce for $1. The difference is your profit, which is $5. The second good to be produced has a marginal cost, the cost of that very second item of $2, and you can sell it for $6. So your profit will be 4. For the third good, you can sell it for 6 and you make it for 3. So the profit on the third good will be, just on that third good, will be $3. On the fourth, $2, right? On the fifth good, the difference between the price and the marginal cost is $1, the profit, the marginal profit, so to speak. And the last good to be produced, you make it at $6 cost and you sell it also for $6. So there's zero profit to be made to be had from the sixth good. Will you make the seventh good, assuming the seventh good is again like the marginal cost for every subsequent good increases by $1, right? So it will cost you $7 to make. The seventh good will cost you $7 to make, and you can sell it for $6. Will it be just reasonable to make that good in your production facility? No, because you will sell it for less than it will cost you to make it. The marginal cost will be more than the price. The price is 6, the marginal cost will be 7 to make that good. Pointless to make it, because what's the point? You will make a loss, that much will be your loss. Not anymore the profit, but the loss. So your optimum production quantity, that's how it's determined, right? Every step of the way you analyze and you compare the market price or the marginal revenue, which is the same thing, with the marginal cost. For the first good, you make the comparison of the marginal cost for the first good with the marginal revenue, the price for the first good. For the second good, you compare the marginal cost of the second good with the price for all the goods. For the third good, you do that comparison of MC versus the price. And whenever the marginal cost is less than the price, your extra production for that very good will generate a profit according to these numbers, right? According to these numbers, you'll make a profit. But then, at the end of the day, when you make the sixth good, or six goods altogether, right? Altogether, what will happen is that the sixth good will generate zero profit. It's just about worthwhile to make it, but the seventh good is not worthwhile to make for you. Totally useless idea from the standpoint of maximizing your profits. Remember, as a businessman, as a hard-headed businessman, your idea is to maximize profits. Profits are set to maximum, right? You have to maximize your profits, and the profit maximization in that situation will be achieved at that optimal quantity of making six goods. Not 7, not 4, but the maximum profit will be when you make 6 goods, and that profit will be $5 of profit on the first good, $4 of profit on the second good, so it's 9 now, plus 3 is 12, plus 2 is 14, plus 1 is 15. So the total profit is $15. That's the maximum profit possible in that setting when you maximize the profit, right? The best idea for that in that situation is to produce 6 goods, not 4, not 3, not 7, just 6. And that production of 6 goods, the optimum production quantity, Q star, will generate you a profit of $15. So what we do pretty much in that analysis, as we went along comparing the marginal costs to the prices, we developed the optimal production quantity of 6 items, right? 6 pieces, so to speak, of goods to be produced, because the market price was $6. And so your total profit was analyzed as the difference between the price on the market and the marginal cost to make just the associated good. For the first good, the marginal cost was $1. For the second good, it was $2. For the third, $3. And you took this difference between the price and the cost. You took the difference, and then you sum up from the first to the sixth good. You summed up individual profits to be made on each good to be produced in that series, right? Individual profits were summed up. When you sum up numbers, of course you can write that you take the marginal profit, that difference is a marginal profit, right, of the first item plus marginal profit of the second item, and we can write like that with many pluses. marginal profit of the third item up to 6. Otherwise, just to abbreviate the notation, you can, that's your marginal profit, right? The difference, right? You can just prefix that marginal profit with a summation sign, that thing, right? That thing. You can prefix it like that, and the notation carries the same meaning. You sum up 6 numbers, the marginal profits for each good to be produced in the series, from the first marginal profit to the 6th marginal profit. You sum up 6 numbers from the first to the 6th, these numbers, the differences, right? And then you sum up and get the total profit. Your total profit is the sum of individual marginal profits up to the optimal production quantity. You sum up and you get the total profit. That's your best profit possible, the profit that is maximized, right? In that situation when your marginal costs are like that. So when you have a limited number of goods, you can use a summation. But what transpires is when you have too many goods, right? Instead of just taking sums, you can analyze the areas under the marginal cost curves. When you have too many quantities of goods produced, these bars become tiny. So here, each bar, has a certain area. The first bar has an area of 1 square centimeter because it's just 1 unit produced at $1. So the area of that bar, right? Notionally, I'm counting in square centimeters, but it's a product of dollars by units, right? $1 multiplied by 1 unit will give you some area of 1, and that bar has an area of 2, right? Because you multiply $2 by 1 unit. This bar has an area of 3 because it's $3 multiplied by 1 extra unit of production. As you shift from producing 2 goods to producing 3 goods, it's 1 extra unit of production. So you multiply the cost of that extra unit of production 3 by 1 unit. Here you multiply 4 by 1 unit, so that area is 4, right? So you use when you sum up your individual marginal profits, by implication you're also summing up areas. You are summing areas equaling 1 by 1, 2 by 1, 3 by 1, 4 by 1. As you sum up these numbers for individual marginal profits to get the total profit, it's equivalent to summing up areas of these bars. This area plus that 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 area, right? And you get 15. Your total profit on optimal production is 15, which is also the area of that stepped figure, right? Stacked set of bars. This area of that stacked set of bars side by side is also $15 by units, meaning it's the dimensionality of that. The measurement is of that stacked set of bars is dollars by units, meaning just dollars. Dollars times many times dollars received is just dollars as well. So your total profit is dimensioned as dollars. Again, it's a quantity, I guess, per period, right? Because we know quantities in economics are flow variables, so it's quantity per week, right? So we should also assume that this is your total profit per week in that instance, per week. Always analyze dimensionalities of the variables you're analyzing to make sure you don't make a mistake. Okay, so we learned one thing. When you sum up marginal profits, it's the same thing as summing up areas. And now it's interesting. When you have just 6 goods to produce, in our instance, our price was 6, so we produced up to 6 goods. You can just sum up according to the summation sign. But when you have too many goods, like not 6, but 600 goods, each having its own marginal cost, increasing in slight increments, will you be summing up 600 numbers, one by one, like 5 plus 4 plus 3 plus 2, and then who knows how many other numbers will be there, and with different values. It's very labor consuming to sum up 600 numbers, even with calculator or in Excel spreadsheet. So instead of running analysis in terms of sums, right, you can do analysis in terms of integrals. So I'm introducing to you the idea of the integral, right? Definite integral. The definite integral counts the area under the curve. Instead of bars, Now we are shifting from the bar presentation of marginal costs to the continuous smooth line for the marginal costs. We have an exercise in this week's tutorial for Friday in which we'll have a continuous curve for the marginal costs. Not bars anymore like in that example, but a curve. So when you have a presentation of marginal costs in terms of curve, you cannot anymore sum up like individual areas or individual values for these bars. You have to take the definite integral, right? The definite integral gives you the idea of an area under the curve. Definite integral gives you the idea of an area under the curve. Effectively, you will be summing the areas of tiny bars. Because if you notice, let's take some marginal cost curve, just some, like from your tutorial for this Friday. That was a tutorial curve for this Friday. And notice what happens. The marginal cost is first increasing in that example, where marginal cost depends on quantity of output produced. The marginal cost keeps increasing first and then declines. So first, the marginal cost obeys the law of diminishing marginal product. And secondly, from that vertex point and to the right, beyond the production quantity of 900 goods, it violates the law of diminishing marginal product because, well, it's just an example. Below, in the production range from 0 to 900, the law of diminishing marginal product asserts itself, and beyond it violates. I don't know why, just an example. Don't ask me why. But well, here we can analyze that marginal cost curve in the domain where the law is upheld and not violated. So in that domain from 0 to 900, we can analyze the situation. Okay, so assume now that it's a marginal cost function, and we want to estimate our production optimal quantity of production Q star, right? That one, Q star, assuming some price on the market, right? Some Q star optimal quantity. What is optimal quantity to be produced? Assuming there's a price on the market. Again, on the y-axis, we not only have marginal costs, but also the market price is plotted as horizontal lines marking off the situation in terms of market prices. So let's say our market price y is whatever it is, $828,000 per unit. That's a price to sell a unit, right? And I think this chart relates maybe to the production of cars, monthly rate of output for cars, and so this is a costly good, right? A car is costing you something to make, and that's a lot of money, and so that's a big production process with big marginal costs and lots of output. So a conveyor production process for cars. I'm imagining that now. And so what is optimal production quantity? Remember, according to the rule of equating marginal costs to prices, right? Comparing first and then equating. Comparing and then equating, we keep on increasing our output as long as our marginal costs are below the price. So in that range where the marginal cost curve is below the price, in that range, right? It's a price and that's marginal cost. So in that range it's below, still below, up to here. From 0 up to that production, it's still below. We can read off the value of the intersection point between the price line and the marginal cost curve. It's actually given here. Yeah, so it's 229, where the price line intersects the marginal cost curve is a quantity of 229, and so to the left of that quantity, between 0 and 229, we will keep increasing output to make more profit, because every time you can sell for a greater amount than the cost, the marginal cost, right, you can make a profit. So our production should be increased up to that number of goods produced per week or maybe per month. So our optimum production quantity is 229 units of goods produced per month. Where the price line intersects the marginal cost curve is that optimum production quantity Q. We know that Q, that one, right, is 229. So that's an answer to the optimal production quantity in that situation in order to maximize the profit. What will be that total profit maximized? Again, we cannot anymore sum up the differences between the prices and the marginal cost for all the 229 units, especially if I do it by hand or on a calculator. It will take me hours and hours of labor to estimate the total profit. But I know that generally the total profit, right, is an area. In a simple case, let me draw a simple case just to make it more visual. We have some marginal cost curve, right? Here we have marginal cost plotted. Here we have the price line, prices on the market, and where the price line from the price on the market originating according to the market situation intersects. It's a straight line. Okay, just I cannot draw it straight with the mouse. But where that line will intersect the marginal cost curve of your production process, that will be your optimal production quantity. That's Q line, right? That's optimal production quantity. And so the total profit will be the area of that shape limited or bounded by the price line above and the marginal cost curve below. And you cannot produce below zero. You can only produce output above zero. So that's a shape, right, of that segment. The total profit of your production is that segment delimited by the marginal cost curve from below and the price line above. So that's the price line on our situation, 28,000, right? And that's marginal cost. Where the marginal costs are below 28,000, well, in that range you still increase your output up to 229 units, right? So we need to estimate that area above the marginal cost curve and below the price to get the idea of the total profit. How to estimate? We cannot just simply sum up with a summation, summing six numbers from the first number to the sixth, because it will be way too time consuming to sum up 229 numbers. So instead of summing up, just mention what is happening. You know, that area above can be developed as an area of that shape, the rectangular shape, the revenue, right? The Q times the price is that revenue rectangle, that shape, and an area of a rectangle is very easy to get. You multiply Q by P. Q is 229, the price is 28,000. And to get the total revenue associated with the production of 229 units, and from the total revenue, the area of that rectangle, you will deduct the total costs. That's an area below the marginal cost curve, right? That area below total. Oh, I changed the color. Very good. This new area below the marginal cost curve and bounded by the axis will be the total cost of production, right? Total cost. The area under the marginal cost curve will be your total cost. And then this area of that rectangle, I told you it will be your total revenue. And the difference between the area of the total revenue, that rectangular area, and the total cost, the area beneath the marginal cost curve, the difference will be exactly your marginal profit, your total profit, right? Your total profit, therefore, is total revenue minus the total costs. Total cost is that black area. Total revenue is the area of the rectangle, very simple to estimate. And the difference will give you the total profit on the production of the optimal quantity. Let's analyze in GeoGebra, very easy. So when you estimate the total area under the curve of the marginal costs, you cannot sum up 229 numbers. So what you do, you use a definite integral. The integral is the area under the curve. That integral essentially is a sum up of these tiny bars. Each has a small tiny area, like very tiny bars are summed up. These tiny profits are represented by tiny bars are summed up, tiny, 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 but when you sum up tiny numbers, they add up to some big number. So tiny bars, their areas are summed up in a pretty much same way as we are summing up these bars of 1, 2 value of area, 3 value of area, each 4 value of area. We can sum, so you can sum up bars of unit area, unit length, right? And then take their sum. These are bars of unit length, and then it's a summation, right, for you, summation. But now we are summing up very tiny bars. very tiny bars here, where here, the areas of very tiny bars. We are splitting, essentially what we are doing, we are splitting that area under the marginal cost curve into millions, thousands, millions of tiny bars, each having a tiny area. And then we are summing up the areas of these tiny bars to get the area of that shape under the marginal cost curve, your total costs, right? That is done, the summation of the tiny areas under the bar, under the curve, is done with the idea of integrals, definite integrals. So when you sum up certain big numbers, we use sum sign, but when we sum up tiny areas, we use a sign for different integrals, meaning we are summing up these areas in the domain where the q for this areas is limited by zero production and the production of 229 units, and we sum according to the area under the marginal cost curve over the domain of RQ. The tiny bars with a width not of a unit, of 1 unit, not unit bars anymore, but the bars with a tiny width in the domain of the change in delta, this delta change, right? Change is delta Q. So we sum up marginal cost by the change in Q. The sign for indefinite integral. In GeoBra, it's very easy to implement. All we've got to do is to type integral, and it's implied when you give a range to the delta Q, when you sum up the area under the curve. It's already implied it's a definite integral. So then you type up, they call the function MC, even without calling the argument of the function, you just call the name of the function, the marginal cost function, to be integrated over that range from 0 to 229, right? That's a notation. We sum up the areas of these tiny bars of a tiny size delta Q in the range from 0, Q of 0 to 229. So in that range of from 0 to 229, there will be millions of tiny bars with a width of a tiny value of delta Q. And the height of each such a bar will be some definite number given by the elevation of the marginal cost curve. And you find the areas of those tiny bars and sum them up. I think, computers, they don't know integrals, protocols for calculating integrals analytically. So actually, what a computer does when it estimates that value of the area under the marginal cost curve is actually, it does literally that. The computer, your machine, does literally that. It splits the area into tiny bars and can calculate the area of each such a tiny bar, and then it sums up these tiny areas step by step. We can sum up. For us, it's difficult to sum up even 6 numbers, but this thing sums up as millions of tiny bars in the range from Q of 0 to Q of 229, your optimal quantity of production. And that's how integrals are calculated. Maybe, I remember it was taking me a while to calculate an integral by the summation automatically, like 20 minutes once. But we are doing that in the cloud, right? So I guess the calculation here went very fast. And so we know that in that example, the total cost, that A is the area under the marginal cost curve, it's a total cost. The total revenue will be given by the area of that rectangle, the revenue rectangle, right? Total revenue. Revenue is equal to 229 times the price of 28,000, right? 28,000. The market price for the goods sold is one and the same, 28,000. And we are getting 6,412,000. The area, the total revenue area. Your total revenue in that instance is that much. And then your profit associated with optimal Q of 229, that area, this will be the difference between the area of the rectangle and the area of that shape. Again, how will we call it with one word? We cannot use 2 words to name. So it's your profit, right? Your total profit, but just we can use one word, so it's your profit. Meaning the difference between revenue, right? We can call the revenue as known. right? Already it's called revenue, so the value of the revenue is known by the computer, minus that total cost given you by that A variable 448 4,449,000, right? So the profit is 1,962. That's your total profit generated on the revenue of 6 million. The profit generated on that revenue is like 2 million, almost 2 million, right? What is the marginality of that optimal production process? The return on sale, right? You have to divide the profit by the revenue, right? The total profit by the total revenue. To get the idea of your marginality, call the return on sales. Return ROS is return on sales, the marginality of your production. Profit by revenue. It's 30% marginality. Return on sales in that instance is 30% at the optimal production quantity of 229. We learned two things, in the first case when we introduced to you the principle of that rule, comparing marginal cost to the price to decide about the optimal production quantity, right? We learned to use a summation sign to sum up 6 numbers according to that, right? Your total profit was given to you as the marginal profit, the difference between the price and the marginal cost, summed up 6 times, like this bars were summed up. This areas beneath, like, let me depict, right? We summed up 6 areas. That area plus that was 5, plus that area that was 4, plus that area that was 3, right? 3, 5, 4, 3, and then that area altogether, the areas of this 5 bars, this area here being 0, right? The areas of those 5 bars resulted in the total profit of 15. So this was a summation process done manually. You do it manually because each bar has a unit width, and you just take the actual distance here between the price and the marginal cost, multiply by unit width, which is 1, and you don't multiply by 1, what's the point? So you just sum up these distances. But of course, summing up distances, we know we are also summing unit areas of the areas of unit width with this elevation. And by implication, when we have many numbers, we can split up, instead of summing like unit areas with summation, we can split up the area above or under the curve into tiny intervals, and that we did in GeoBra with you, right? In GeoBra, we did integral to find the area under the curve. Instead of summing, now, instead of using that sign like before, now we are using that sign, the sign for definite integration. Okay, and by the way, that rule about the marginal cost curve as compared to the price is a rule about your individual supply curve, right? It's very important because we also know that what is the individual supply curve? It's an association between your P and Q, right? How much you are prepared, how much you will apply at a given price. Your commitment to supply, for example, at that price, that many units of goods, right? At that lower price, will supply less goods. Q0, Q1, so there will be some curve. So that's an association between your price at which you will be selling and your preference to supply that many goods at that price, or that many goods at that price. An association between P and Q is your individual supply curve. The supply curve is the same thing I'm repeating as a marginal cost curve, because according to the rule of MC set equal to P, right, we already associate the market price with the quantity, right? We associate according to the profit maximization rule, where the price line intersects your marginal cost bars or marginal cost curve, whatever it is. It can be bar or a curve, a set of bars or a curve rather, right? Then whenever there's intersection between the marginal price the price line and the marginal cost curve, that is your optimal production quantity, right? Q optimal. At some other price, say the price declines from that level of 28,000 in our last example, maybe to 20,000. At the lesser price on the market, given your marginal cost association depicted by these bars, you will stand ready now to supply less of the quantity of goods, less of the quantities of goods. like not 6 anymore, but just 4. So this is an association between your P and your Q, right? At certain price, your optimal production quantity is your Q. At other price, at some other price, it's some other quantity. Same thing as a supply curve for you as an individual producer. So by definition, therefore, there's a certain identity between the marginal cost curve and the supply curve. Very important. These two things numerically at least are identical. Not just equal, but let's say even like numerically identical. That's identity. According to that rule. Again, if you observe that rule, if you behave according to how that rule of comparing marginal cost to the prices prescribes you to behave, right? It's a prescription, you behave according to the prescription, then your marginal cost curve or a bar is the same thing as your individual supply curve. Very important. Okay, what else have we discussed that week? We discussed a little bit about the law of diminishing marginal product, right? And the status of that law was with respect to microeconomics, that as you work your variable quantity, variable production factors worked upon fixed production factors. As you keep on working fixed production factors with variable factors, you generate your output. And the marginal output, the additional output keeps declining, right? It was a low diminishing marginal product or the low diminishing marginal returns in microeconomics that is observed over the short term of market operations, right? Over the short term of market operations or a time frame of analysis, but implication is a short-term period because you have some fixed factors and some variable factors. The variable ones working the fixed ones, the output is declining in terms of the marginal product. That's a low diminishing marginal product. But what about that law in terms of macroeconomy? Not micro anymore, but what about that law in terms of macroeconomy? The Coase-Douglas production function, I mentioned to you that, right, in teaching week 2. We can just copy paste and from that link and see that function. Just to refresh, the Coase-Douglas production function is a macroeconomic production function. Yeah, that was your Coase-Douglas production function. GDP went here, GDP, right? Then your that was your capital here, your labor here. On the axis, you can take a cross section of the Coase-Douglas production function, and you can cross sect it according to a certain value of capital, keeping the value constant, right? Capital value is constant. We have a slider for that. Here, I guess, let's set the capital value at $46 million of capital in the national economy. And then with that cross section, we have an association between not two inputs, but just one input for labor, capital being kept constant. So that association, just let me disconnect and take the cross section. This cross section of the Coase-Douglas function with the capital held constant at that rate, at that value. K is cross sectioned at that value, and so now the cross section with respect to labor and GDP appears to be that one. Yes, as you can see, the product, your GDP, the total product, it first increases fast, but then the rate of increase gets less steep and less steep. The tangent line being the presentation of your derivative. The tangent line is the slope of the tangent line is the value of your derivative at the point where the tangent line touches the curve of GDP by labor, the cross section of the Coase-Douglas function, right? As we can see, the steepness of the curve, the tangent line, or by implication the value of the derivative declines, and because it declines, the marginal product of labor is getting less and less. You put in an extra dose of labor, and with an application of every extra dose of labor to the production process on the national level, your GDP grows up by less and less. Progressively, your GDP increases by less and less as you keep adding more labor into the production function. Yes, so this macroeconomic function of Coase-Douglas variety has a property that it illustrates the law of the diminishing marginal product, not just on the microeconomic level. The Coase-Douglas production function is a macroeconomic concept. So that's an illustration of the law of diminishing marginal product on the macroeconomic level. It also applies. However, it's a very grim law. It's a very grim law, right? Grim. because if it applies, it means we are doomed to macroeconomic collapse, because at least not so much a collapse, but the profits will disappear in the economy. And like political economists of the day in the 19th century, even Keynes, they believe that it will eventually happen, that because of that law of diminishing marginal product, all the profits will evaporate from the economic machine. The economic machine of a national economy will settle down into the steady state. The steady state at zero profits, right? All the profits in the industry, in business, everywhere will be evaporated. Steady state, it's called, right? The notion or the specter of a steady state was a big specter of that tormented economists, up to Keynes, up to the century, up to the 20th century, right? And Keynes, I think he wrote a pamphlet called The Economic Possibilities for Grandchildren. And he said, yeah, they're going to live in the steady state. No profits in their industries once the grandchildren live. They will not have no profits. And that's our age, right? Keynes wrote that in 1929 or in the 1930s. So, he was speaking about our age. He was hypothesizing that we will be living in a steady state where the marginal product is zero, so the profits evaporate. We just reproduce our current economy. But this thing didn't materialize. That green prophecy of a steady state at zero profits never materialized, because historically, it was observed, according to the research, that in the Cobbs-Douglas production function, if you take notice of the function, it not only has this inputs for labor and capital, it also has a total factor productivity component, the A factor, the total factor productivity, or sometimes it's called, when it's estimated, it's called the sole residual, and that was kept growing at the average rate of 1% per annum, right, across all the 42 economies from that period to that period for almost 90 years, right? In all the big economies, the A factor, the total factor productivity was increasing at that rate. So that situation, that A factor thing, right, it saved the day from the inevitable impact of the law of diminishing marginal product on the macroeconomic plane. Had we had this law being fully in effect, we would have been living in a steady state, a very grim reality for businessmen. But it never materialized, precisely because of this A factor changing its value over 100 years. Why was it changing its value? As you can see, in the past 50 years in the United States, in the second half of the 20th century, right? GDP was not so much driven by labor and capital increments as by the change in that A. So this is the red line for GDP change, and the blue line is the solar residual, this A factor change. So the blue line drives the red line, the solar residual, the A factor, the total factor productivity drives your GDP. Essentially, it's shown here, and that's because of that situation, right? That AT, the total factor productivity, keeps increasing. We are saved from the onset of the steady state, from the onset of the grim reality of the law of the diminishing marginal product on the macroeconomic level, right? That situation saves the day. Why does it save the day for us for so long now? For 100 years. Well, because Schumpeter, and he's a very famous economist after all, Joseph Schumpeter, he's a famous one. He's an entrepreneurial economist. All the entrepreneurs, they name drop this name, right? Schumpeter, he's very famous by proving that innovations, the bundles of innovation on the macroeconomic level, they are responsible for the fact that we keep on staving off the effect of the law of the diminishing marginal product almost for 200 years now. Because of innovations, because of the total factor productivity, the entrepreneurial component associating labor and capital, right, the total factor productivity, the A. Because of innovations driving that growth in A, we are being yet, so far, for at least for 200 years, so far we are being saved from the effect of that grim law of the total diminishing the law of the diminishing marginal product on the macroeconomic level, right? We are still saved from the pernicious impacts of that law. We haven't yet reached the steady state because that's not possible. The steady state is not possible. There's a notion of creative destruction. Again, this notion is due to Schumpeter. The notion of creative destruction operating in the economy. With innovations, with bundle of innovations coming on stream, First of all, steam power here at the dawn of industrial revolution, then electric power, the internal combustion engine, the information technology revolution. These bundles of innovation, they deliver in a great way. First, they take off, and then because there's an explosion of growth in these technologies, all these technologies, right? Then because of the explosion of growth, the law of course is not operational anymore. And then this technology, in terms of its returns, in terms of their contribution to GDP, that impact dies off. The technology, the impact, the explosive effect of technology dies off, flattens out, and now we would expect the law of diminishing marginal product to set in. But no, the next technological innovation or a bundle of innovation comes on stream and takes off explosively. And then as it dies off, another bundle of innovation takes off and delivers the growth in GDP and the staving off of that law and creation of profits. The new innovation then again comes and takes over and delivers, and we are believing these days that this is just a natural kind of natural thing, that innovations come in bundles. For 200 years it was like that always. We were saved from that onset of the grim law of diminishing marginal product by this reality of innovations coming in bundles, coming on stream every 50 years or so. We have some new revolution in the industry. Now it's, I guess, sixth technological revolution, as they call it, sixth technological paradigm associated with sustainable technology, the green power. That's what is believed to be the case now these days. Again, this new bundle of innovation with climate technology, green technology. Until that, it's the current situation propelling the economic machine forward with its sense of innovation. That's why the governments are so eager to encourage green technology, sustainable revolution, these technologies to achieve the zero, what is it called, zero carbon future, right? By 2050, right? Maybe these technologies are not about achieving zero carbon emissions, they're more about actually stimulating the economic growth through entrepreneurial technologies associated with hydrogen, those zero green technologies, zero emission green technologies. That's a lot about energy. And energy, of course, is the foundation of the economy. All these industrial changes, industrial revolutions have as their basis the change in the energy input to feed our economic machine, right? And I guess this day and age, that's a green technology, that's a green energy based on hydrogen. But still, that's what is happening. It's believed we are going to be saved from the grim reality of the future when the steady state is there. We are going to be saved from that steady state by these innovations, continuing every 50 years or so. I'm not sure if you believe in that, but that's an idea due again to that creative destruction perception developed by Joseph Schumpeter, very famous. He died in 1954, and this school of entrepreneurial economics is solely due to him. And we have neo-Schumpeterians now, and this is a chart from a recent book from 21 by Carlota Perez, right? Technological Revolutions and Financial Capital. You can read that one, it's quite interesting. So thank you for your attention. That's what I wanted to convey for this week, and bye-bye.